first order of business, I want to correct myself regarding a statement I made last time. So I was partially correct, but I confused you a little bit with the statement regarding boundary conditions, the number of boundary conditions for a partial differential equation. So yes, I stand corrected. The number of boundary conditions is consistent, should be consistent with the highest order derivative in your differential equation. So if you have a first order in space partial PDE, you need an initial condition for sure, but you also need one boundary condition for that partial differential equation. However, you must distinguish between boundaries and boundary conditions. So in a spatial domain, in a domain where you're solving the PDE, you could have 1,000 boundaries. You could have 50 inlets on one side and 100 outlets on the other side. However, at each boundary, you only require, for the advection equation, for example, you only require one boundary condition. So what is the difference between a boundary and boundary condition? A boundary is a physical specification, physical location where a quantity exits or enters, where there's a flux of a quantity going out or into your domain. But a boundary condition is the mathematical specification of what is happening to that quantity at that boundary. Okay? So with the 1D advection equation we did, we had two boundaries because we were dealing with a finite domain, but we only needed one boundary condition at each boundary. Okay? So you said we needed two boundary conditions. No, really, we need one boundary condition, but one for each boundary. So a total of two boundary conditions, but one per boundary. So you have to be careful. If you're doing a diffusion equation, in principle, you need two boundary conditions, okay, to be able to specify, to properly specify the solution. Okay? All right. So last time we did a lot of coding, and I hope that I haven't posted the Jupyter notebook yet. I just need to clean it up and before I post it. But you should have the recording if you want to kind of repeat what we did. And I hope you're getting some mileage with that. You're playing around with the numerical solution. Today we're going to try to do two things. We want to, as the title says, we want to look at the advection diffusion equation, and I'll explain why. And secondly, we want to do three things. So look at the advection diffusion equation, and using the advection diffusion equation, I want to introduce to you some basic properties or basic analysis tools for finite difference methods. So essentially evaluating errors, looking at consistency, convergence, and stability. And we will look at the Lax-Richtmyer equivalence theorem and what that means. But we will also want to do a two-dimensional version of the advection equation. Because remember, our goal now is to head to the vorticity stream function formulation. If you remember your homework, the vorticity stream function formulation got rid of the pressure from the Navier-Stokes equations, and you only dealt with vorticity and stream function. And given an initial condition for vorticity, you solve for the stream function, solve vorticity transport equation, and then repeat, rinse and repeat. Okay? So this is what we're heading, but that's a two-dimensional problem. So we want to get some mileage on doing a 2D problem. It's not that much more complicated than the 1D, but it is. I mean, the curse of dimensionality can just be very nasty. Okay, so let's get started. So the Navier-Stokes equations, the vorticity transport, the vorticity stream function formulation, if you look at them, they're really advection diffusion equations with source terms, right? And typically, so as we are starting to study the Navier-Stokes equations, we can't just go ahead and solve them. Because if something happens in the solution, we're not going to have any idea why that thing is happening. So it makes sense, and that's been kind of what we preach in CFD and numerical methods is, let's work with model equations first. And the model equation, we did the model equation with the advection equation. Today we're going to do the advection diffusion. It makes sense, right? Because the Navier-Stokes are advection diffusion equation. Okay, except we're going to deal with the linear version of the advection diffusion equation, and that looks like a time derivative, so an accumulation term, also as we call it, an advection term, and a diffusion term. So now you should know that a first derivative means advection, a second derivative means diffusion. Advection moves things in space. Diffusion spreads things in space. Okay, and the nonlinear version of this equation, known as the Burger's equation, would have a u over here rather than a constant speed. So you'd have a nonlinear term for the advection term. Okay? Now, over the weekend, I was working on doing an exact solution for the advection diffusion equation, and stumbled upon an interesting kind of finding. Obviously, it's for sure done before, but anyway, an exact solution for this equation, one exact solution in a periodic domain. If you are given an initial condition a sine omega x, omega is the frequency in space. So in a domain from 0 to 1, you can have 2 pi. So you have a peak and a max and a minimum, and then you could do 4 pi, increase the frequency, right? So for this initial condition, what would you imagine the solution to be? Okay, so we have a sine wave. We're going to subject that sine wave to advection and diffusion at the same time. So what do you expect the solution to behave like? Yes, a moving wave that is shrinking. So the moving wave, we know how to do it. That's the exact solution of the advection equation. So essentially x minus ct. And how do you dissipate? An exponential decay. So you take that and multiply it with an exponential decay, and you get actually an exact solution for the advection diffusion equation. Simply, you take the initial condition and you move it in space at the speed c, and you also scale it with an exponential term minus mu, that's the diffusion coefficient. Notice the omega squared here. Now, later on, we're going to look at this in way more detail, but the presence of omega squared, if you had a higher frequency signal, so omega was 100 pi, that is going to dissipate much faster than a signal that has 2 pi. Okay, and it's just an observation. Keep that in mind for the future. So this is what the solution looks like. It advects and just decays in time. Okay, pretty straightforward, simple. A numerical scheme now for this advection diffusion equation. If I want to do forward Euler in time and central in space for both advection and diffusion. Okay. So now, if you remember last time, if we did not have the diffusion term, this scheme, the FTCS scheme, forward in time, central in space, blew up, right? The solution. Solution was unstable, was unconditionally unstable, and we did the analysis. We showed that the leading term in the truncation error had a negative diffusion term, which was unphysical, and that's why the solution is going to just grow in time. Okay. However, I claim that once you add a diffusion term to the governing equation, although we are using a central scheme on advection, this term is going to combat the negative diffusion that is introduced by this term. Now, there's going to be a fine line where you choose delta t and delta x where this is okay. But the addition of a physical diffusion term is going to allow us to combat the instability that came about from the negative diffusion of using a central scheme on the advection term. So then we can use a central scheme here, and we're going to use a central scheme on the diffusion equation as well, okay? On the diffusion term as well. And so this scheme looks like this. Do you want to implement it together? You kind of know how to do it by now, right? Because this is just the addition of one extra term, okay? And you treat the periodic boundary conditions like we did last time, okay? And just for your benefit, I put in the code. You can just copy and paste it from the PDF and just play around with it. So it looks exactly like what we did before. But however, I define an additional number that's mu delta t over delta x squared. I call it the NFL. That's the mu or MFL diffusion number, whatever. And the CFL is the advection, the coefficient for the advection term. So that's so this guy is the CFL, and this guy is the NFL or the MUFL. Okay. And This is exactly what we had last time, just only up to the central, to the advection term, and you just add a diffusion term. Okay? Pretty straightforward. Okay. So I did this morning, and now I just picked a random delta t and a random number of points, and the dots represent the numerical solution. The solid black line represents the analytical solution. And obviously, for this combination, the solution just blows up at the end. OK, so I'm going to keep the number of points fixed, and I'm going to cut delta t in half and see what happens. If you do this, your solution is a little bit more stable. But then it's not exactly kind of spot on, right? So the goal of these slides is to look at accuracy now, OK? And you not only see a difference in decay, you also see a phase shift. You see that the max and min, they're a little bit off compared to the analytical solution. So there are some numerical effects going on. So obviously, we can also, let's try to cut this in half, even, the time step in half. And you get a little bit better accuracy. It is decaying. It is actually, there's a phase shift. It is lagging a little bit in time, but it's much better than this guy. So, you know, how accurate can we get? Like, we can keep decreasing delta t all the way to, what, 10 to the minus 4. Look at this. This is kind of nearly spot on. But obviously, there's, and I did decrease also the spacing over here, or increase the number of points. But obviously, there's a point of diminishing returns where if you, the more you refine, you're not going to get any benefit. Can you tell me why? So if your computer can represent, let's say, 6 digits in a number, okay? So the best you can do is with a combination of delta t and delta x that gives you that amount of accuracy. Anything beyond, it's not going to give you any benefit because the computer is just going to chop it. So it's not going to be useful. So obviously, yeah, we can refine our delta t and delta x, but there's going to be a point of diminishing returns. So how can we see this? How can we see this? We're going to look at errors. Okay? So this is the first step towards understanding how our finite difference schemes behave, how our numerical solution behaves. So how do we define an error? So for this problem, we have an analytical solution. We have a numerical solution. So can you help me define an error? Okay, that's correct. So in this case, I'm going to define the pointwise error, lowercase ei, as the exact solution at point I. So I take the exact solution, evaluate it at point I, minus the numerical solution at point I. Obviously at a fixed time. Okay, so we pick a time, we run, we pick a time, take u exact minus u numerical. Okay? Now, that is going to give us a vector of errors. Pointwise, at each point, you're going to have an error. Okay? Now, you can plot that error, but that's not really descriptive. What we are looking for is how an average, the error on average, in an average sense, decreases as we refine our delta t or our delta x. Okay? So what is a mathematical quantity that allows us to take a vector and convert it into a single number? Magnitude or norm. So error norm. So there's a more general term than magnitude, and those are error norms. I'm going to define 3 error norms for you. And I'm going to call this the L1 norm, the L2 norm, and the L infinity norm. The L1 norm just simply takes, assuming constant spacing, takes the spacing and multiplies it by the summation of all errors. So that's going to give you one number. You scale it with delta x. The L2 norm is the square root of delta x times the summation of the errors squared. So you take each error, square it, take the summation. That's going to give you one number, multiply delta x, take the square root. The infinity norm, which is my favorite norm, I always use the infinity norm, it just takes the maximum value, okay, of the error. Now, be very, very careful about this scaling. For those in the back, you probably haven't seen this before, and that was why you were having problems when you were doing sometimes order of accuracy analysis, so you end up doing the L infinity norm. Go back to all your codes and make sure you put this scaling in and see how your codes are going to work. And that's going to be a homework problem. I'm going to ask you in your homework, what happens to the error when you do not include the delta x? Okay? So we can obviously use this to examine both spatial and temporal errors. The temporal errors are a bit kind of harder to examine, but they follow a similar strategy to examining spatial errors. So in the interest of just moving forward, I'm going to focus on spatial errors right now. So to examine spatial errors, so remember the truncation error for a general for the general PDE. I should have put that on my slides. So the truncation error, TE, looks like, you could imagine it looks like, you know, C1 delta T to the P plus C2 delta X Q plus some other terms, right? So how can I get rid, if I want to examine only the error, so the error in my solution, when I take the difference between the analytical and the numerical solution, I'm going to get this guy. Do you agree? Of course, yeah, I'm going to get that guy. But I want to look at that truncation error as I refine delta x. So how can I get rid of that term? One way to do it is to pick a very, very small delta t, such that it's always smaller than delta x to the q. So pick the smallest delta t you can think of. And typically, there is some sort of art over here, or trial and error. You pick a bunch of delta t's, and you see, you know, what happens at different delta t's you refine in delta x. So we're going to fix delta t now, pick a very small delta t and fix it. And we're going to refine delta x and look at how the error converges or diverges or doesn't do anything anymore, right? If our numerical implementation is correct, the error, or the log of the error, remember the first, one of the first slides, should, on a log plot, 1 over delta x and log of error is gonna, or error on a log plot, is gonna decrease straight line with a slope of delta x cubed, the order of accuracy. So a second order in space scheme is gonna converge, as slope is gonna be 2. First order slope is gonna be 1, okay? So we're gonna pick a very small time step and refine the grid spacing. Now, I put the code that does this for you. If we have time at the end, we can come back and see it. But essentially, what I'm doing here, I'm declaring an array of number of grid points. So essentially, I want to test this for 21 points, 41 points, 81 points, 161 points. Always have that one at the end because finite difference and then intervals. Or you can just create a log space of points. Okay, so that gives you, 10, 20, 46, whatever, just a bunch of number of points. And for each one of those, for each entry in that array, you solve the problem. Okay, you just go. So for n in n points, for each number of points, delta t is 10 to the minus 4, very small, and then domain, etc., all of these things, you just solve the problem for this n. Then at the end, you take this, I'm taking here the L2 norm, np square root delta x times the norm of u numerical minus u exact. Okay? Now be very careful to evaluate this at the same time. If you evaluate your analytical solution at t plus delta t and your numerical at t, you're going to get an additional error that is going to dominate. Okay, so be very careful. Make sure that you are evaluating everything at the correct time. Okay? So I make sure of that by making sure that I add t plus delta t and I know what u nu means. Okay, I alluded to that last time. And then once I get the error at this grid resolution, I save it into a vector of errors. Okay, and then you just plot. Okay, so you can just copy and paste this into your Jupyter notebook and just run it as is. Okay. So what happens? This is a log plot, so we should have error over here and 1 over delta x, or number of grid points. So what I'm showing here are 2 reference lines. The orange line is a line with a first order slope, and the green line is a line with a second order slope. So if our error is converging at the correct rate, remember we are using second order in space for both advection and diffusion. So we should expect a delta x squared error. So our error should decrease as we refine delta x. Our error should decrease at that same rate, or with a second order accuracy, it should have a slope of 2 on this log-log plot. So our error line should be parallel to the second order line, and it is. Okay, it is. So remember here, we have the largest error, that's like about, what, 10 points. And then as we pick more points, our error decreases. So you cut the spacing in half, your error is going to be reduced by a fourth, okay, because it's delta x squared error. But then we get to this point, where like no matter how much we refine in delta x, we're not gaining anything in the convergence of the error. Okay? So in fact, if you continue, this is just going to do this and just maybe even blow up. Not because your numerical solution is wrong, but because the difference, your numerical solution is so accurate that the difference between the numerical solution and the analytical solution in the eyes of the computer is indistinguishable. So when it takes that difference, any round off term is just going to magnify. Okay? And then when you take the norm, that's just going to blow up. It's like dividing by 0, essentially. Okay? So that's what's happening here. You just do not get any benefit. So this is the point of diminishing the returns. And there's a way we can analyze where you hit that point. But essentially, you know, for this delta t, this is the highest grid spacing you can benefit from. So don't expect to just slap any, you know, number for delta x and delta t and just say, yeah, this is the most accurate solution. It is stupid to run your solution here because your computer is not benefiting from any of the additional accuracy, okay? This is not saying that your numerical solution is wrong. No, it is as accurate as this point. The points over here show as straight lines because they are indistinguishable from the numericals, from the analytical solution. So essentially, the error is 0. So that's why you see a straight line. Okay, your error is 0. Is this clear? It is 0. It is 0. The error is 0 in the eyes of the computer. So the computer cannot represent any more numbers here. And on a log-log plot, what's a line with slope 0? It's just a horizontal line, right? So really, your error is 0 over here. So don't confuse that by saying, oh, you know, there's something in my numerical solution. No, there's nothing wrong with your numerical solution here. It's just, so if you go to the computer and print new and print exact for up to 16 digits of precision, you're going to be like, I can't, all the digits are exactly the same. Okay? And any round off is going to dominate. So oftentimes you see wiggles over here going up and down. That's because it's because of this round off. When you take that difference, all the digits are correct except for the last digit maybe, and in the eyes of the computer, that's just going to blow things up. That term is going to dominate, okay? Okay. So now you know how to conduct an error analysis for a finite difference scheme where you have an analytical solution. Later on in class, you're going to tell me, or I'm going to tell you, well, you don't have an analytical solution all the time. So how do you make sure that your code is accurate to the advertised order? So you can come and tell me, I wrote a code that is 4th order accurate in space and 2nd order accurate in time. I will tell you, prove it. So how can you prove it to me? First, you do it, you apply your code to a linear problem where you know the exact solution, so that gives you enough confidence. But for a nonlinear problem where you don't have an analytical solution, there's a strategy that allows you to kind of get an idea of your order of accuracy, if indeed your order of accuracy is still valid for the nonlinear case. Okay? So that's the best we can do. The method is based on systematic refinement. So essentially, you solve the problem over here, and you use that essentially as your exact solution. Okay, you solve it numerically at a very fine grid level, and then you do it for the coarser grid levels and compare to the fine grid level. And you do this systematically, you can capture the convergence rate. Anyway, that's for later time. Okay, the point is, as long as accuracy is reasonable, and as long as you are satisfied with the results, there is no reason to refine your time step size or your grid resolution just for the sake of refining it. Okay, as long, in fact, it is inefficient to time step at very, very small time steps if you are within a stable, if your solution is stable and you have reasonable accuracy. Okay, because there are other things other quantities that are of interest to you. Okay, is this clear? Yeah. Yes. Yes.
Is there a method for finding the crossover?
That's a great point. You will see that crossover when you do.
Do you understand what I'm saying?
Yes. So you have to do it systematically. So you create like a table. You refine delta t, refine in delta x, and you do your plots. And you'll oftentimes see where that breakpoint between delta t and delta x is. Yeah, but it is actually, and so there's a method where it does kind of systematic refinement delta t and delta x, and then solves a nonlinear system, which is an optimization problem where you can kind of. But your goal is to get the order of accuracy, not just find the sweet spot for delta t, delta x. Just get the order of accuracy, because in practice it's really hard to do this. In practice, we rely on the stability conditions from linear analysis. So, the condition that C delta t by delta x is less than 1, we use that on the nonlinear equations, although it is not accurate. So we say, let's multiply it by a safety factor of 50%. Okay, so we take half of that. But I'll try to add a lecture on this a little bit later, because it can get really entangled doing the order of accuracy. You can stuck in order of accuracy analysis forever, but in the end, that's not the point. Okay. Okay, but as long as accuracy is reasonable, it's desirable to step at a satisfactory solution. So don't go overboard with your selection of time step size and okay. However, when we saw earlier that different schemes combined with different equations, we cannot just take arbitrarily large time steps or large grid sizes, because we saw something that we called instability. Okay, so you started with a good solution, and then you saw the solution just grow in time rather than dissipate in time. So today we're going to slightly formally define stability, one of the first properties of finite difference methods. So how do you understand stability? How do you understand? If I tell you this solution is unstable, the error or the solution just grows unbounded. So what about a solution? So I'm going to take. What about? So we said that an unstable solution, if this is kind of at a given time, if this is the solution, then an unstable solution is just going to look like this, where these guys are just going to blow. Okay. What about a solution that over time follows kind of this line but looks like this? But is it stable? Yes, it is stable. Okay? And we're going to look at these in more details. This is called dispersion. So essentially, although your solution is pretty far from the exact solution, it is not unbounded. It is bounded and stays within bounds. Okay, so distinguish between oscillatory and unstable. Unstable, solution is going to blow up. That is the simplest definition of instability. Now, mathematically, numerically, the way we can define this is say, is the error at the new time step, if you introduce an error at a time step n, This error could be from round off, from a boundary condition, from anything that shows up in the solution, really. Your solution, the solution itself. If you introduce something, is that thing gonna, how is it gonna behave in time? Is it gonna grow unboundedly? Is it gonna remain constant? Or is it gonna dissipate? So the condition for stability, we want that thing, epsilon n plus 1, the new value of that error over the old value, to be bounded, to be less than or equal to 1, really. To be not more than epsilon n. At worst, it will be equal to epsilon n, so or an error or a signal, right? But even better, we want it to decay in time, because you don't want that to pollute your solution. So this is one definition. A finite difference scheme is said to be stable in a naive sense when errors from round-off and or truncation do not grow indefinitely in time. So before we look at PDE stability, I want to look at ODE numerical stability. So in ODEs, you may have learned about stable ODEs in the continuous sense, essentially. I'm not talking about that. I'm talking about the numerical solution of a ordinary differential equation. So, and this is just to illustrate the idea of oscillation versus unbounded behavior that I mentioned before. So consider the following ODE, du dt equal minus u with an initial condition u0 equal 1. Okay, so the exact solution for that guy is u of t is e to the minus t. And indeed, at t equals 0, this is equal to 1, e to the 0 equal to 1. Okay. Now let's apply a forward Euler method for this guy. So un plus 1 minus un over delta t equal minus un. So you get un plus 1 equal un minus delta t un, which is 1 minus delta t un. Okay? That's a single time step. So now let's look at un plus 1 over un. Okay, so we said, what is the solution at the next time step compared to the solution at a current time step, or a previous time step? Un plus 1 over un, we want that magnitude, an absolute value, to be less than or equal to 1. So this implies that actually the magnitude of 1 minus delta t less than or equal to 1. You do the analysis, it tells you that as long as delta t less than or equal to 2, this guy, this ratio is less than 1. So let's see what happens. What I'm showing here are 4 curves. Follow me first. So the exact solution is shown in blue. Okay, so it's that nice line. Then the orange line shows the solution with delta t equals 0.5. That's the orange line. You see there's an error between the orange line and the blue line, but it kind of follows the trend nicely. Then the green line, I picked the delta t equal 1.5. It is still less than 2. But look at it, the green. It is oscillatory, but then kind of decays, right? So this line is still stable, but is not really an acceptable solution, okay? But it is stable. Now, if I pick dt 2.1, that is slightly greater than 2, look at the solution. It just actually grows in time, okay? It just grows in time. So this is kind of a naive, a simplistic view of instability based on ODEs, okay? Now, the reason that this delta t, the reason that if you want to get rid of oscillations, you can further the analysis by looking at, okay, so if un plus 1 is 1 minus delta t un, this is a recursion formula. Un is 1 minus delta t un minus 1, and un minus 1 is 1 minus delta t un minus 2. You do this all the way, and you get un plus 1 is 1 minus delta t to the power n times the initial condition, okay? Give or take n and n. Now, we know from basic kind of analysis that this guy needs to be actually less than 1 to avoid oscillations in your behavior, because n is going to go 1, 2, 3, 4. It's just going to go up and down, okay? So if you make delta t less than 1, then you make sure you get rid of your oscillation. Okay, this doesn't really translate to our analysis, this last piece, but this is a great example of stable versus unstable versus oscillatory. So this is oscillatory but stable. This is oscillatory and unstable. And typically they go hand in hand. An unstable scheme is going to be oscillatory most likely, okay? So how do we apply something like this to a partial differential equation? So last time we did a truncation error analysis, and we looked at the first term, okay? But usually that's not enough. And we were lucky with the advection equation and upwind that all the terms in the truncation error looked like 1 minus c delta t over delta x to the power n, essentially. So all the terms were similar, so we were able to draw the conclusion that you want c delta t over delta x less than or equal to 1. But that's not often the case. So, and the truncation error analysis can be tedious because you need to get all the terms and find kind of which term is what is the stability, and it can be really annoying. Okay, there is another way. There's another way to do this, but it is limited to linear PDEs. And is that a problem? Not really, because it's those PDEs that give us insight. We can do complex eigenvalue analysis, and you just get a bunch of numbers and trends, and you just have to squint at it to understand what is going on. But these linear PDEs are going to give you a firm foundation, a firm understanding of how the different quantities compare. In a way, it's compared to each other. In a way, it's going to give you a closed form solution of your stability analysis. Okay, that's what they do. The approach is called the von Neumann stability analysis, and we're going to apply it to the advection equation with forward in time and central in space. So we showed last time that this is unconditionally unstable because it has negative diffusion in the leading order term. Okay, but still that's not a proof, right? What if you had a higher positive diffusion in one of the higher order terms? So it's not enough, really. It wasn't a good proof. Okay. So the idea here is we want to do the same. We're going to look at the amplification of the solution in time, so un plus 1 over un. But if you just do this un plus 1 over un, it's really not going to help you algebraically. So what we really want is to use the power of Fourier. And if you remember your Fourier analysis, the idea behind Fourier series or Fourier analysis is that you can represent any function, specifically periodic functions. You can represent them using sines and cosines, or you can combine the two and represent them with exponential series. Okay? So essentially, you can write any signal. So this is uj at point n, and I change the index here to j because I need I to represent the imaginary unit. Okay? So at a grid point j, ujn, so that's u at xj at time n, is represented by this discrete Fourier series going from minus infinity to plus infinity. There's a coefficient, epsilon kn, times e to the ik xj. Okay, what this is saying is that this is a signal in space, the e to the ik xj, that represents a signal in space that is multiplied by something that changes in time. Notice there's no time in this term. I is the imaginary unit, k is the wave number. So if you can go back to your kind of basic math, engineering math analysis, and see how you do this. This is legit. You can just put this in Python, take any signal, put it in Python, and get all of these coefficients. Okay? This is legit stuff. And we're not making this up. So imaginary unit times a wave number, so this could be 2 pi m over L, for example, times xj, the location in space, times something that changes in time. Now this thing is a function of k, the wave number. So for each, so this is the summation. For each wave number, you're going to have a coefficient over here. Now, we're going to take this guy and put it back here. But since this equation is linear, what is valid for the entire summation is actually valid for a single wave number k. Agreed? Just put the summation. If it's valid for the entire summation, everything is linear, it's actually valid for an arbitrary wave number k. So we can figure out the solution for a wave number k and then add everything up together. Okay? So instead of doing the summation, we're going to drop the summation and say ujn is just epsilon k to the n times e to the ik xj. Okay? So then what happens to uj plus 1n? We simply augment xj with a delta x, right? we started by we're assuming constant spacing, like from several lectures ago. So you just j plus 1 is xj plus delta x, right? So this is what you get, epsilon e to the ik xj times e to the ik delta x, okay? And then you j minus 1n, same thing, you subtract delta x from xj. And you get this e to the minus ik delta x. Clear so far? Okay. So now we're going to take these guys and put them into the solution. Now what we've effectively done here, we've ripped out space, we've moved from the real domain to the frequency domain, but that has tremendous benefits in essentially isolating the frequencies. Fourier analysis is gonna show us how frequencies interact with each other and how frequencies can lead to instability. So it gives us a unique insight into a solution. Okay, when we are looking at this, we're looking at the total solution. You can't distinguish like which part of the signal is really messing things up. But when you go to Fourier, it's going to tell you how the different frequencies interact with each other. Anyway, so when you substitute this back, you get epsilon n plus 1. This is all at wave number k, so we can even drop the k over here. So you get epsilon n plus 1, e to the ikj, e to the ikxj, everything here. So this is just substitution of these guys into here. Okay, so we are after un plus 1 over un, or in other words, epsilon n plus 1 over epsilon n. Now remember, when we looked at the Fourier series, this is just something that changes in space, and this is something that changes in time. So really, the space distribution is not going to be that as much as important as the change in time for stability. Okay. So now we can simplify. Okay, so let me see. We can simplify. What did I do here? I copied it twice. Okay, so never mind. So we're going to simplify e to the ik xj. Okay. So that gets rid of e to the ik xj. So now we're left with the effect of delta x. See how we ripped out? We just are focusing now only on the effect of delta x, and we have a delta t, and we're looking for epsilon n plus 1 over epsilon n. So we're going to divide by epsilon n. So you get epsilon n plus 1 over epsilon n. You get a 1 over here minus c delta t to delta x, and this guy. Now this is a trigonometric identity. It's equal to 2i sine x. Okay? There's actually a 2i over here. What happened here? So anyway, so there is a 2i over here. So this trigonometric identity, the exponentials, the difference, oh yeah, that's right. So the difference is actually a 2i sine k delta x. And so now we have this ratio, okay? So we're almost there. So we started with a finite difference version of the PDE, okay? We substituted a form of the error. Now we're looking at the ratio of error at n plus 1 over error at n, or solution at n plus 1 over solution at n. So for stability, we want this ratio, we call that the amplification factor. Remember that definition? The amplification factor is the ratio of your solution at n plus 1 over your solution at n. Okay? So we want that, the magnitude of that, to be less than 1 for stability, or less than or equal to 1. Okay? But now we've expressed this ratio just in terms of delta t and delta x. See how great this is? So now we have a relation between, we can derive a relation between delta t and delta x, okay, for stability. But we still have this I. So typically what we do in this case, we actually take, now this is a complex number. This G is a complex number. So to evaluate magnitudes of complex numbers, you take their squares, which is a really easy. So what's the square of what's the magnitude of a complex number, or the square of a complex number? So if you have A plus IB squared, that's A plus IB times A minus IB. That's equal a plus b squared, a squared plus b squared. Okay? So if we take g squared, that's going to give us 1 plus the square of all of this. And you can immediately tell that, well, if g squared is greater than 1, because the sine is bounded between, sine squared is bounded between, is bounded between 0 and 1, right? Sine squared is bounded between 0 and 1. So at best case, this is equal to 1. Worst case is greater than 1. Okay? So really, g is the square root of this quantity, which is greater than or equal to 1 for any delta t or delta x. So that's why that scheme was unstable. We call this unconditionally unstable. There's no condition for which this scheme is stable. Okay? So I'm going to ask you to apply the same analysis for when you do the upwind scheme. Okay? So last time we did it with the truncation adder. That gave you some insight. Now I'm going to want you to do it with the amplification factor. Okay? Now I'm going to take this and give you the result for the advection diffusion equation. The advection diffusion equation is much harder to do. So typically we just quote the result. I may give it to you as an exercise. It's really annoying to kind of derive, but it's doable. For 1D, you need to satisfy two conditions on delta t and delta t over delta x squared. And you see how the diffusion coefficient factors in and the wave speed factors in and the diffusion coefficient. So you need to satisfy your choice of delta t, delta x needs to satisfy both of these conditions. Okay? For diffusion alone, this is what you get. So if I ask you in your homework to do the diffusion equation in 2D, for example, this is what you should get from the amplification factor. But when you combine advection and diffusion, it gets a little bit harder. So in 3D, it's even much worse. Okay? So what we often do, we use these conditions for the Navier-Stokes equations. Because, you know, trying to figure out your stability as you are solving the nonlinear system is probably as costly as solving the equations themselves. You know, so we may as well just start with a guess and take a safety factor around that and see how far we can push. Okay. Oftentimes we take a time step, and if we find it's unstable, we go back and restart. Okay, and take a smaller time step. Those are the perks of, you know, CFD in practice. Okay? Okay. So stability, we understand. Can someone summarize stability to me? Okay, so a scheme, a finite difference scheme for a linear or for a differential equation, really, is stable as long as the solution does not grow unbounded, or any error that is introduced in the solution does not grow without bounds. So sometimes you may have source terms that may, you know, cause an increase in your solution, but that increase should be bounded and just kind of stabilize. So you have a kind of reaction, for example, which is going to spike your temperature. Temperature is going to spike, but then it's going to stabilize. Okay. So stability doesn't always mean diffusion, you know, or dissipation of the entire solution. It means it is bounded, really. Okay. Now the second property of finite difference schemes is called consistency. Now this may be a little bit esoteric and kind of somewhat obvious to you, but a consistent finite difference scheme means that the truncation error of the finite difference scheme does actually go to 0 as you take delta t and delta x together to 0. Okay? So in a way that kind of makes sense, because all we've done is derive finite difference schemes from Taylor series. So the majority of finite difference schemes are consistent. Another way to formulate this is that the finite difference operator tends to the continuous operator as delta t and delta x approach 0. But anything you mess up with in your finite difference scheme can lead to an inconsistent scheme. And being numerics people, sometimes we introduce an arbitrary term to stabilize our solution. So you saw Josh's talk last week. The introduction of that additional term, is that a consistent So one of our PhD students is working on a very complex problem, and he had to introduce some form of a relaxation, some term in his discretization. Now that term stabilized the solution, but it may not be a consistent term in the sense that as delta t and delta x, as your grid spacing, as your resolution approaches 0, or infinite resolution, you're not going to recover the original equation. So I'll give you an example. The advection diffusion equation, our truncation error looked like delta t delta x squared. As delta t looked like this, order delta t delta x squared, or a delta t times delta x. Okay. As delta t and delta x approach 0, the truncation error does indeed approach 0. What's an example of an inconsistent scheme is when the truncation error looks like delta t delta x, and there's a term that has delta t over delta x. As delta t and delta x approach 0, this term is not determined. This term is only 0 if delta t approaches 0 faster than delta x approaches 0. So delta t has to be delta x squared. So then you have another condition on the scheme for it to be consistent. Delta t has to scale with delta x squared, for example. Okay? And possibly in the homework, maybe, so there's this scheme called the Dufour-Frankel scheme that is inconsistent. Okay? It's an inconsistent scheme. So it does get a solution, but it is not consistent with the governing differential equation. Okay, so consistency may be kind of a little bit esoteric to you right now, but I promise I'll fix the idea in a couple of slides. There's one other idea in finite difference methods, and that's convergence. So what is convergence? Don't look at the slides. Look at me. Okay, so we talked about the error through the consistency. Convergence has to do with the solution, not the consistency. Convergence says that the solution of the numerical scheme, okay, approaches the exact solution as delta t and delta x approach 0. That's not equivalent to the truncation error approaching 0. So can you give me an example? So don't confuse convergence with consistency. They may sound similar, but they're not. And actually, you do know of an example that is consistent, but that does not converge. Advection equation, forward in time, central in space. Truncation error approaches 0 as delta t and delta x approach 0. It is a consistent scheme. We recover the governing equation as delta t and delta x approach 0. But the solution of the difference scheme does not converge to the solution of the PDE. It blows up. It converges to something else. It diverges. So there's a difference between consistency and convergence. So you can have a consistent scheme that doesn't converge. But then what is the missing term between? So the FTCS scheme for advection is consistent but does not converge. Why? Because it's unstable. So there you go. You have this triad of consistency, convergence, and stability. And they are so tightly related that there's actually a theorem for that. It says that for a linear partial differential equation, a consistent finite difference scheme will converge to the exact solution of the PDE if and only if it is stable. So I double if and only if, or I double IFF, means it's a necessary and sufficient condition. So stability is a necessary and sufficient condition for a consistent scheme to converge. Okay, so there you have it. That's the trio. Lax equivalence theorem. Okay? Although it wasn't really discovered by Lax, he kind of alluded to it, but later on, people figured this out, with von Neumann analysis, etc., and then Richtmyer, and then they called it the Lax equivalence theorem. It's really this kind of triad of things together. Okay? All right, so this is what I wanted to talk about. Okay, so we still have some time to do the 2D case. So this is what I wanted to talk about, finite difference methods. So that gives you just enough grounding in terms of how you can evaluate an error, what's instability, what's consistency, what's convergence. Those will be hard to do for nonlinear equations, but you should try. You know, they're part of your arsenal now. You have an equation, try to do a Taylor series, try to analyze consistency and these ideas and see, you know, they actually do apply to nonlinear systems pretty darn well, okay? Now, in the next few slides, I'm going to try to do the 2D advection equation. But first, I want to give you a very practical tip regarding implementing periodic boundary conditions. So last time, I told you, so if you remember, we wrote the code, and we said, okay, we solve only on the interior of the domain, and then at the end of the domain, if the wave is moving to the right, we just specifically apply the finite difference equation at that point and pick up the periodic points in that term. Do you remember that? And then, pardon me, and then we take that value and set it at the at point u0, if you remember that. Remember? So if you want to see, so I can actually go back and code. Just going to show you. Okay, so if you look at this slide, if you remember this guy here, these two lines. So first we solved the problem on the interior of the domain. So we had point 0 and -1 unsolved for. Then we looked at point -1, and we applied the equation for, you know, central scheme. But then we also said, okay, ui plus 1 at that point is equal to u1. We picked the periodic boundary, and then we took that value and put it at u0. There's a smarter way of doing this, a cleaner way of doing this. I'm going to show that to you right now. So rather than doing this, okay, so again, I'm going to switch to logical human indexing. If this is your domain, so u1 and un, these are your boundary points, okay? These are your boundaries. Last time, we created an array of n points, okay? But what if we actually add an imaginary point on each side? We call that a ghost point or a halo point, okay? So now our array is of size n plus 2, 1 point on the left and 1 point on the right. And then what you do in your solution process, you actually put your periodic boundary values at those ghost points. So you take u2 and put it here, remember, because un is equal to u1, right? So this term, this point is u2, okay? And then you also take un minus 1 or u minus 2, or actually minus 3 now, and put it over here. And then all you need is one formula. U from 1 to minus 1, okay? So that's going to give you this subset, and you just, bam, apply your discretization scheme. And after you do this, you update this point, and you update that point. I see some folks frowning. Who doesn't get it? Okay, so what is standing in the way of? If you write it down, okay. So we're going to actually try to code this. But I wanted to do it because that is going to be really helpful in 2D. In the two-dimensional case, can you imagine the nightmare of trying to figure out, or in 3D, can you imagine the nightmare trying to figure out which point to pick? So if you solve it on the interior, and then you go at each boundary face where you have nx, ny, or ny and z points, and just trying to reason around that, it's insane. So this is a much cleaner way. This only requires you to solve it on the interior plus the boundary points, and all you have to do at the end is update the points that are outside your boundary, and that is done with a simple assignment, you know. u minus 1 is equal to u3, because this is 0 now. 0, 1, 2, right? And u0 is equal to u minus 1, minus 2, minus 3. That's all you have to do. Okay? So I'm going to go and try to implement this for you. Again, for the advection equation in 1D, and then we're going to quickly try to do it in 2D. Okay? Okay. So let us see. New window. Let's see if I can get the local host. Okay. CHEN 2450. And lectures. Let's see. I want you to see my lectures and my homework. It's all a mystery. Okay. Let's see. This is the 2D case. Okay, so I'm going to create again a new notebook. And just kind of, are you guys, is this, can you see? Okay, so we'll just pick a standard set of rules and then create a linear space, etc. And just define an initial condition. This is our initial condition. Okay. And let's do the upwind scheme. Okay, so I'll show you the previous way we did this, the old way of doing this. Just to double check that actually works. Okay. Okay, so that was the solution with upwind, okay? And it kind of decays in time as expected, correct? Okay. And what we had to do was we did the interior, right? Interior points un plus 1 equal un minus c delta t over delta x ui minus ui minus 1, okay? Now what I'm going to do, instead of creating an array of size, what I'm going to do, I'm going to create an array. U is equal np dot zeros of size n plus 2. Right? So I have n points, including the domain points, but I want 1 point on the left and 1 point on the right, so I have an array of n plus 2 points. Now for the initial condition, because the initial condition was created using only n points, why? Because x was created with only n points, okay? Remember, the outside points I don't care about, really. They're just kind of temporary points. So now that I've created an array of n plus 1, n plus 2 points, I only want the points from 1 to n rather than 0 to n plus 1. I want the points from 1 to n to hold the initial condition. So then u from 1 to minus 1. Okay, so that is going to give me now the subset, all the points excluding the ghost points. That's equal to u0 of x. Okay, and then I'm going to initialize my solution with u. Okay, if you're not clear about that, you can just test it separately, and then you can do plt.plot u, and you see that's the 0 from u equal np dot zeros, but then all the points on the legitimate domain excluding ghost cells are legitimate. Okay, all right, So that creates the initial condition. Okay. So now un is sol minus 1. That remains the same. U new is un dot copy. So we're going to create a hard copy. Now this remains the same, right? Because this is just saying ui n plus 1 is uin minus c delta t delta x times uin minus ui minus 1n. Except that now 1 to minus 1 actually covers the boundary points as well. Okay? We still need to do one thing though. Fill the ghost points with correct values. Okay? So let's start with the last point, u nu minus 1. What is that going to be in terms of Python indexing? Remember, 0 is the ghost point, is the first ghost point in terms of Python indexing. We have 0 and then the boundary and then, the first interior point. So in terms of Python indexing, this is 0, 1, 2, da, 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 da. Again, in terms of Python indexing, this is minus 1, minus 2, minus 3. So so if we take this and put it here, this point coincides with that point. So minus 1 coincides with 2. Okay? Is this clear? So I'm going to move point 2 and put it here. So I'm going to say u minus 1, u nu minus 1 equal u nu 2. Okay? And then, since this guy should be equal here, so this guy coincides with this guy, then we move to the left. u0 is actually u minus 3. Clear? No. When you do the slicing, it's open bracket. When you do a point, it is the correct point. It is the point in question. So it's actually equal u minus 3. Right? So u0 is u minus 3. So let's see. Now remember, this solution includes the ghost points. I don't want to plot it with the ghost points included. So what I'm going to do here, as I do the animation, I'm just going to pick the points that exclude the, let's see what happens. Same exact thing. Isn't this cleaner? We only had to do one formula, which was identical to our finite difference formula, the mathematical form. That is the power, yes? We didn't have to. I did because here's what happened. So yes, that's a good point. So yes, what Elizabeth is saying is just so happens to work here. So what Elizabeth is saying is that we actually have to do this on the initial condition as well. That is correct, and I have that on my own notebook here. So thank you, Elizabeth. Luckily, it didn't cause any problems. Okay? All right, so this is going to be really helpful for the 2D case. We have 5 minutes to do the 2-dimensional case. I don't think we're going to be able to do it. Okay. How about we do it on Thursday, and then we apply it on the vorticity transport equation. Okay. I wanted to give it to you as a homework, actually. So this is the 2D advection equation. The only thing that's going to change, the things that will change now, are actually you're going to have 2-dimensional indexing. Okay. So really, what happens here is that. So then you have an x and y and all sorts of kind of nasty points. So let's do it together on Thursday. I really want to kind of try to guide you through it. No, actually we have until 12:05, right? For the class. Yeah, so we have about, yes, yeah, we have about 10 minutes, 10, 12 minutes. Okay, so let's do this for 2D. All right. So 2D two-dimensional advection diffusion or advection equation. Okay, and the formula is just simply this guy. This is the formula. Uij n plus 1 it's the same thing as the previous one, but now you have two terms. And we're going to do upwind for both of those terms. So you see upwind in the x direction, it's ui minus 1. J is fixed. And then uij for the y direction, j and then j minus 1. Okay? That's assuming u and v are positive. Okay? That's what we're going to start with. Okay, so what do we need for this case? We need points in the x and y direction. So nx, let's say, equal 21, ny equal 21, lx equal 1, length in the x direction, ly is 1, also length in the y direction, x and y direction. Now, x is mp.lin space from 0 to lx with nx points, and y is mp.lin space 0 to ly and 1. So that's only going to give us a one-dimensional locations for x, one-dimensional locations for y. But what I really need is xy, yes. Yeah, what I really need is xy in 2D, not just at a line. So there's a neat function in Python, just like MATLAB, called mesh grid, okay, that combines x and y and creates a grid for you. So that's what I'm going to do. First, let's define dx equal lx over nx minus 1, dy, not doing anything special here, just like we did in the 1D case, okay? And then let's create a grid of coordinates. So then we have x, y equal mp dot mesh grid xy. So then if you want to see what x looks like, this is it. X is only increasing in the x direction, but it's the same in the y direction. And then if you want to show the y, same thing. Y is constant in the x direction, but also, well, Python transposes that. Really, so what you want is .tt. So never mind. Python transposes that. It puts, for our physical space, our coordinates start from here, then positive, positive. In Python and MATLAB, it starts here and goes positive and positive. Okay? So don't worry about that. Okay. So now, for the numerical solution, I am going to create, so it's very simple with advection equations. You just translate the initial condition. So what I'm going to create now is an initial condition, 0 times 2 pi times np dot pi. And my initial condition is going to be u0 of x and y. Okay. Who has not seen the lambda? You've all seen the lambda. It's a quick way to define functions, okay? So I want an initial condition function of x and y. That's going to be mp dot sine omega 0 times x times np dot sine omega 0 times y. Plot the solution, the initial condition. plt dot contour f. So I'm just going to use contour lines x, y, u0 at x, y. So that's the initial condition. And let's see. Okay, so that gives us the initial condition. It's just a sine and cosine wave combined together, and we want to advect that kind of diagonally. Okay. Okay, great. So now let's get into some numerical specification. We want the advection in the x direction, cx equal 1.0 and cy equal 1.0. We'll start with equal velocities. Just going to pick a delta t 0.01, just because I did the exercise earlier. And you just have to pick delta t such that c delta t by delta x is less than 1, the smallest of the x and y velocity, okay? You pick the smallest delta t. Okay, so dt is 10 to the minus 3, t end, you just run it for 2 seconds, and initial time is t equals 0, and then CFL1 is cx times dt over dx, CFL or CFLx, CFLy is cy times dt over dy. Okay, we'll set up the initial condition. So solution is equal, that's going to store our solution, numerical solution. And then I'm going to create now an array with 2 ghost cells in each direction. So 2 ghost cells in x, 2 ghost cells in y. Same idea applies when we recycle the periodic conditions, okay? So u is np dot zeros. I'm going to create a 2-dimensional array, nx plus 2 and ny plus 2, okay? And then u 1 to minus 1 and then 1 to minus 1 is equal to u0 at x, x, y, y. Is this clear? So we've picked, since we created u0 only from excluding the ghost points, I'm just going to set the values that exclude the ghost points to that initial condition. But there is one caveat here that you have to keep in mind when you are doing 2-dimensional arrays in Python. So in 1D, the indexing was I, right? There was one set of indices. In Python, for 2D arrays, this is I and this is j. So this is the indexing in the x direction, and this is the indexing in the y direction. You would assume that this is the indexing in I and this is indexing in j. It's not. It's the other way around. And same thing for 3D. I, j, k. Okay? So just keep that in mind. When we do uij, in Python, it's uji. Okay? Just keep that in mind. Okay, so now we do what Elizabeth asked us to do, set periodic boundaries for the initial condition. Okay, so how are we going to do this? Okay. So you have this 2-dimensional grid, okay? And you have this halo around it, halo of points around it. So this is our physical domain with grid points, okay? So we have solution variables, solution values over here at all of these points, okay? You know, you have etc. Gonna have a grid, right? Okay, and we have a halo of points around it, right? Because we created a ghost cell in each direction. So that is the effect of having a ghost cell. Okay? So let me just kind of fill this up. So these are the interior points plus points at the boundary. And these are our ghost points. Sorry about the low quality drawing, but I'm trying to do this really fast. Okay. This guy. Okay. These are the halo points. You can extend. We typically kind of put dotted lines right here. Okay. For periodic boundary conditions, let's start with the x direction. In our nomenclature, in CFD nomenclature, we call this phase the x minus phase, and this phase the x plus, this phase the y minus, this phase the y plus, z minus, and z plus, okay? So let's start with the x plus phase. These points, all of them, all of these points, we're going to take all of these and just put them in here. just like we did with the 1D. Okay? Including these guys or not, it doesn't matter because those are going to be reset correctly. Okay? And same thing for these points. We're going to take these guys. Okay? In other words, this is going to go there, and this is going to go here. So here's what we do. For the x minus phase, actually I'm going to start with the x minus phase. So for the x minus phase, what is the x minus phase given by? What is the index for the x minus phase in Python indexing? It's u, everything in the y direction, but only the points at I equals 0. Okay? So I equals 0, this is it. I equals 0. Remember, so we start indexing from 0. So all of these points, I equals 0, but everything in j, that's this guy. Right? Because we said this is ji. Okay? That is going to be equal to these guys. That's going to be equal to u, everything in the y direction. Same thing with what we did in 1D. Minus 1, minus 2, minus 3. Okay? So u, everything in y at I equals 0 is equal to u, everything in y at I equal minus 3. Same thing for the plus phase. Everything in y at I equal minus 1, and then everything in y equal u2. So that's exactly the same thing that we did in 1D. So u minus 1 is u2, and u0 equal u minus 3, right? So that's u0 equal u minus 3, and u minus 1 equal u2. Except now we need now to swap this as well. So this is for x minus, and then we do this for x plus. Now it gets much easier because all you have to do is swap these indices for the y minus and y plus phase. Pretty simple. So for the y minus, you just swap these guys. Oops. Okay? Is this clear? So y minus phase, you're fixing j and taking everything in x. J equals 0 and everything in x. And you just blindly swap the indices. And really, this is it. Once you figure this periodic boundary condition stuff, the solution is pretty straightforward. Solve.append u. And now we do the solution. So while t less than t end, un is sol minus 1. So it's pretty much like this guy. So let me just copy it from here. Okay. Let me just copy it. Oops. I copied it again. Okay. So sol minus 1, u new equals un dot copy. Now what's going to change here is we have two-dimensional indexing. uji is equal, so uji n plus 1 equal uji. So again, you're going to have double indexing, okay? Minus cflx. Remember, this is ji. So I is going to change for this x direction. So this remains ij, right? So, right? And then all we have to do here is say this is j I minus 1, correct? Minus CFLY times, I'm going to get this guy, and swap the indices. This is u, this term is uij, and we want here ui j minus 1, okay? So I'm just going to swap the indices, okay? And then what do? We set periodic boundary conditions. Now, I want you to try to imagine the nightmare of doing this without ghost points. You would have to go and pick the points at the different boundaries and just try to reason. You would have 4 more formulas actually 6 more formulas at the bottom. And that's really annoying. This is much easier, much more elegant, okay? I hope you're convinced of that. Get rid of this, call this U new. Okay, 1208, I apologize. I'm dragging you for, what's CFLY? Unexpected indent. Oh, of course. Okay, finally, we can now animate the solution. I have this little fancy animation thing over here. Pretty almost there. Okay, almost there. CM is not defined. Import from matplotlib import CM. This is all cosmetic stuff, okay? So fingers crossed. Still running. There's a much more complicated animation. Should have run it for like 0.5 seconds. Anyway, what I'm doing here is just essentially collecting contour plots and specifying a color scheme, etc. Okay, look at that. It's only advecting in the x direction because we made a mistake. Why is it advecting only in the x direction? CFLY is CY. DM is 0.5 seconds. I think the new line messed things up. Okay, there you go. Look at that. Isn't that beautiful? Advecting in 2D as expected. Okay? And also diffusing. But to see the diffusion, so I'm going to throw on you some practical tips. You're going to be doing maybe some simulation in your grad school. I often see PhD students standing up and showing this contour map with like 1,000 points on the color bar, like -1, -0.99999, -0.99999. This is useless. This is crap. Just pick like 3 or 4 points over here. Make sure you fix the damn thing so that we know how it's changing in time. So I fixed this between -1 and 1 based on the initial condition, and that is going to show me that the solution is actually decaying in time. Oftentimes you see animations with a changing color map. Unless you intentionally want to trick your audience that your solution is actually not diffusing, don't do that. Fix your color map, maybe based on the final solution or based on the initial condition or based on an average number, but make conscious it's displaying your results is as important as getting those results. Okay? All right, sorry for keeping you up. Next you're gonna be doing this for the advection diffusion equation. We're gonna be doing the same thing for the vorticity transport in 2D. Okay? From now on, we're gonna be doing a lot of 2D. Thank you. I hope this was helpful.
So, in terms of like the animation stuff, are you going to like post that?
Oh yeah. I will post all of this stuff so that you can just copy and paste, because I copied and pasted it from someone who copied and pasted it from someone who copied and pasted it from someone. So, and then you fine-tune it to your liking, right? So you have to adapt it to what you like. But yes, I will post these notebooks. Sorry, I'm a little bit behind on these notebooks. So if you're stuck, just come back to the videos and try to kind of type it up yourself, okay? Who hasn't done 2D in previous classes? Or who has done 2D in previous classes? Have you done 2D in grad numerical? Do you remember? For the final project? In what class? Grad numerical, you did 2D? Okay. So 2D is a different animal. It's not that much harder, but makes you think about things differently, right? Makes you think about how you want to implement it nicely, okay? So I hope this is helpful. We're not going to do 3D because it's just essential like 2D. Going from 1D to 2D is a big step, but from 2D to 3D is not that much harder, okay?